Welcome. Let your shoulders sink into wherever you are resting, and let your breath settle into its own unhurried rhythm. There is nothing to do now but listen and drift. High above, spanning the dark, turns the Milky Way, a barred spiral galaxy, its stars gathered into sweeping arms that curve outward from a bright central bar. That shape took shape over billions of years. Gravity slowly drawing gas and starlight into the pinwheel we now call home. Somewhere between 100 billion and 400 billion stars call this galaxy home. That range is wide, and it stays wide, because counting every faint star hidden behind clouds of dust is nearly impossible from where we sit inside the disk. Astronomers instead measure the galaxy's total mass and brightness, then estimate how many stars must be scattered through it. Even at the low end, the number is larger than every grain of sand on every beach on Earth. The Sun rests inside the Orion Arm, a smaller spiral arm tucked between two grander ones. It is not a major arm like Perseus or Scutum Centaurus, but a modest bridge of stars and gas, sometimes called a spur. Our solar system drifts along this arm together with countless neighboring stars, all bound in the same slow orbit. It is a quiet corner of the galaxy, unremarkable in size, yet it is the corner we call home. 100,000 light-years, that is roughly the width of the Milky Way's shining disk. Light itself, the fastest thing there is, would need 100,000 years just to cross from one edge to the other. Our entire solar system, wide as it feels to us, would vanish as a single point of light within that vast expanse. The scale is difficult to hold in the mind, and that is all right. It is enough simply to feel its size. At the very center of the galaxy sits an object astronomers call Sagittarius, a star, a supermassive black hole hidden behind thick veils of gas and dust. It cannot be seen directly, since no light escapes its grasp, but the stars orbiting nearby reveal its presence. Those stars swing around it at astonishing speeds, tracing paths that let astronomers map its invisible pull. It anchors the galaxy's rotation quietly from a place we will never visit. 4 million suns worth of mass are packed into Sagittarius, a star compressed into a region smaller than our solar system. To hold that much matter in so small a space is difficult to imagine, yet gravity manages it effortlessly. Stars passing nearby feel its pull and are flung into tight, fast orbits, some completing a full loop in just a few years. It is the heaviest single object anywhere within the galaxy. 225 to 250 million years. That is roughly how long the Milky Way takes to complete a single rotation. This span is sometimes called a galactic year. The last time our solar system was in its current position relative to the galaxy's arms, dinosaurs had not yet appeared on Earth. Everything turns here, but on a time scale so vast that a human lifetime barely registers as a flicker. The Sun has circled the galactic center roughly 20 times since it formed, 4.6 billion years ago. Each orbit, or galactic year, carries our solar system through different regions of the Milky Way's spiral structure. On some of those journeys, we pass nearer to dense star-forming clouds, on others, through emptier, quieter stretches. We are, in a sense, only 20 laps into a very long and ongoing journey. Star formation inside the Milky Way continues even now, producing new stars at roughly 1 to 2 solar masses each year. That pace sounds modest, but across hundreds of billions of existing stars, it slowly adds more, generation after generation. Clouds of gas and dust collapse under their own weight, sparking new suns within scattered stellar nurseries. Compared to the galaxy's more turbulent past, this is an unhurried, ordinary rate of birth. Beyond its own boundaries, the Milky Way belongs to a wider neighborhood called the local group. This gathering of galaxies drifts together through space, bound loosely by gravity across millions of light-years. Within it, our galaxy is one of the two largest, sharing the neighborhood with dwarf galaxies, faint satellites, and one especially large companion still waiting to be introduced. It is a modest cluster of galaxies, adrift together in the dark. Let your breath lengthen now, just slightly, the exhale trailing a little longer than the inhale before it. There is no need to control this, only to notice it happening, wave after wave, on its own rhythm. Each breath out can carry a little more of the day's weight away with it, leaving your limbs heavier against whatever holds you. Nothing needs your attention right now except this simple, unfolding rhythm of air moving in and air moving out, again and again. More than 80 galaxies belong to this local group, most of them small and faint dwarf galaxies scattered across the darkness. Many are so dim that they escape detection until modern telescopes tune to their faint light. They drift in loose formation, some no larger than a modest cluster of stars, others merely smudges of ancient starlight. Together they form a hushed gathering, spread across millions of light-years, bound only by gravity's steady pull. Andromeda stands as the largest galaxy near our own, a vast spiral neighbor visible even to the naked eye on a clear, dark night. It has shared the same cosmic neighborhood as the Milky Way for billions of years, evolving along a broadly similar path. Astronomers have studied it more closely than almost any other galaxy beyond our own, using it as a mirror to understand our own structure. In many ways, it is the sibling most like us in this corner of the universe. Light now arriving from Andromeda began its journey about 2.5 million years ago, long before humans existed on Earth. That is the distance separating us, roughly 2.5 million light-years of empty, star-strewn space. It is close, by galactic standards, yet still almost incomprehensibly vast to any human sense of scale. When you look toward it, you are looking backward across a stretch of time larger than our species' entire history. Roughly 1 trillion stars fill Andromeda's spiral disk, several times the number found within the Milky Way. That number is difficult to hold in the mind, more stars than there are grains of sand on every beach combined. Its greater size gives it a stronger gravitational pull, one reason it draws so much attention from astronomers. Even at its great distance, its light and mass tell the same story of extraordinary scale. Triangulum Galaxy ranks as the third largest member of the local group, smaller than both the Milky Way and Andromeda, but still substantial in its own right. It lies roughly 3 million light-years away, forming a loose triangle of light alongside its two larger neighbors. Evidence suggests it may already be gravitationally linked to Andromeda, caught in a slow orbital dance. Its spiral arms, though faint from Earth, host their own nurseries of newborn stars. The Large Magellanic Cloud circles the Milky Way as one of its brightest satellite galaxies, visible to the unaided eye from the southern hemisphere. It sits at a distance of about 160,000 light-years, remarkably close as galaxies go. Rich with gas and young stars, it glows with a pale blue-white haze against the night sky. Its gravity has already stirred subtle ripples in the Milky Way's disk, evidence of the two never quite leaving each other alone. Sagittarius dwarf galaxy is currently being pulled apart by the Milky Way's gravity, its stars stretched into a long, faint stream. This stream loops around our galaxy multiple times, a ghostly trail left behind by a smaller galaxy slowly being absorbed. Astronomers trace its path today by mapping the older stars scattered along that stream. It offers a preview, on a smaller scale, of the kind of gravitational unraveling larger galaxies may someday share. Dark matter halos surround galaxies, like invisible envelopes, reaching many times farther than the visible disk of stars within. Neither the Milky Way's halo nor Andromeda's ends, where their light does, both stretch outward into much emptier space. This unseen material outweighs the visible stars several times over, shaping how galaxies move and rotate. Its presence is inferred entirely through gravity's effect, since no telescope has ever captured it directly. Vera Rubin, an American astronomer working in the 1970s, measured how fast stars orbited within spiral galaxies and found something unexpected. Stars at the outer edges move just as quickly as those near the center, a pattern that visible matter alone could not explain. Her careful observations became some of the strongest evidence for dark matter's existence. It was a discovery made through careful, repeated measurement, one that reshaped how astronomers understand galaxies today. Gravity ties the Milky Way and Andromeda together, across a gulf of 2.5 million light-years. Though separated by such distance, the two galaxies are not adrift from one another. Their mutual pull has shaped their motion for billions of years already. Together with their smaller companions, they anchor the gravitational heart of the local group. This bond will only tighten with time, drawing the pair nearer with each passing age of the universe. Let the weight of your body settle now, arm by arm, into whatever is holding you. Feel your shoulders sink a little deeper, released from anything they were carrying. Your legs grow heavy and warm, unmoving, like stones resting at the bottom of a still river. Even your hands loosen their grip on the day, fingers unfolding, palms turning open. Only the surface beneath you remains, holding all that weight without asking anything back. In 1912, an American astronomer named Vesto Slipher pointed his spectrograph toward Andromeda and noticed something curious in its light. The wavelengths were shifted toward blue rather than red, unlike most distant objects Slipher had studied before. At the time, no one yet knew Andromeda was a separate galaxy at all. It was still called a spiral nebula. His careful measurement, made through a modest telescope, would later prove essential to understanding our galactic future. Edwin Hubble, working just over a decade later, confirmed what Slipher's shift had only hinted at. Using observations of variable stars within Andromeda, Hubble showed it lay far beyond the Milky Way's own boundaries. This settled a long-running debate among astronomers about the true scale of the universe itself. Andromeda was not a nearby cloud of gas, but an entire galaxy of its own, vast and distant. That inward shift of light told astronomers something remarkable. Andromeda was not receding from us, as most distant galaxies do, but drawing closer instead. Space itself is expanding almost everywhere, carrying galaxies apart from one another across the universe. Andromeda defies that broader trend held by the gravity, binding it to our own galaxy. Its blue shift became one of the earliest clues that our two galaxies share a future together. Andromeda closes the distance at around 110 kilometers each second, a steady approach measured across decades of careful spectroscopy. At that pace, the gap between the two galaxies shrinks by that same distance every single second, night and day, without pause. It is a motion far too slow to notice by eye, yet fast enough, given enough time, to reshape two galaxies entirely. For decades, astronomers could measure Andromeda's approach along our line of sight far more easily than its sideways drift across the sky. That sideways motion, called tangential velocity, required detecting almost imperceptibly small shifts in stellar positions over long spans of time. Without knowing it precisely, predicting the exact outcome of a future collision remained genuinely difficult. Only the most patient, long-term observations could hope to capture so subtle a motion. In 2012, astronomers combined years of Hubble Space Telescope observations to measure Andromeda's sideways motion with new precision. This improved data allowed researchers to model the future collision far more confidently than ever before. Their analysis suggested the two galaxies were on a near head-on course, rather than a distant, glancing pass. It marked one of the clearest confirmations yet that a merger truly lies ahead. The Gaia satellite, launched to map the positions and motions of over 1 billion stars, later added its own precise measurements of Andromeda's movement. Its data refined earlier estimates, sharpening astronomers' confidence in both the timing and geometry of the coming encounter. Each new observation narrows the range of uncertainty a little further, though questions about the exact nature of that future meeting remain open. Just how massive Andromeda truly is remains difficult to pin down, and that uncertainty ripples through every prediction of the merger's outcome. A more massive Andromeda would pull harder, arrive sooner, and merge with greater intensity. A lighter estimate would soften the encounter considerably. Astronomers continue refining these mass calculations, knowing that even small revisions can meaningfully shift the story's ending. Two astronomers, Thomas Cox and Avi Loeb, built one of the earliest detailed models of the coming collision in 2008. Using computer simulations, they traced how the two galaxies might approach, swing past each other, and eventually merge into one. Their calculations offered a rough timeline, spanning billions of years. One of the first attempts to visualize the future with real numbers behind it, it became a foundation for later, refined studies. To study such a slow-motion collision, astronomers turned to what are called many-body simulations, digital models that calculate the pull each star exerts on every other star nearby. Every simulated star moves according to those combined forces, its path recalculated again and again across imagined stretches of time. Through this method, researchers can watch, in compressed form, how billions of years of orbital motion might unfold. Somewhere beyond this room, a low hum rises and fades, like wind moving through unseen branches, or an old house settling into itself. You don't need to name it. Let it arrive, hold for a moment, and drift away again, the way sound does when a room grows heavier with sleep. Each time it fades, let your body sink a little further into the mattress, borrowing its stillness for your own. Running these simulations demands extraordinary computing power, since tracking billions of simulated stars across billions of years is no small task. Supercomputers divide the work into countless steps, each one recalculating the shifting positions and speeds of every star involved. Even with modern processing power, researchers often simplify certain details, grouping stars into larger clusters to make the calculations manageable. The results still capture the broad shape of what may come. Early studies once left open the possibility that the two galaxies might simply pass by each other, never actually merging at all. With limited data on Andromeda's sideways motion, some models allowed for a near miss rather than a direct collision. That small chance of avoidance lingered in the scientific literature for years, a reminder of how much rested on measurements, not yet precise enough to settle the question. Better measurements gradually closed off that possibility. As instruments grew more sensitive and datasets accumulated, the sideways motion of Andromeda came into sharper focus, and models converged on a direct, head-on trajectory. What once seemed uncertain now stands as one of the most confidently predicted events in galactic astronomy. The two galaxies are set on a collision course. Far across the cosmos, a pair of galaxies called the antennae offers a living preview of what such a collision looks like. These two spirals are caught mid-merger right now, their shapes stretched into long, luminous tails of stars and glowing gas. Located roughly 45 million light-years away, they show astronomers, in real time, the kind of chaos and beauty that awaits our own galaxy someday. Watching real collisions like this helps astronomers test whether their models of the Milky Way's future hold up. By comparing simulated outcomes to what telescopes actually observe in merging galaxies elsewhere, researchers refine their assumptions about gas behavior, star formation, and the reshaping of galactic structure. Each observed merger becomes a kind of natural laboratory, further confirming predictions made from equations alone. A small red star, named Gliese 710, is expected to drift unusually close to our solar system in roughly 1.3 million years. Though it will not collide with anything, its passage may nudge distant icy bodies in the outer solar system, potentially sending a few comets tumbling inward. It's a reminder that our solar neighborhood, too, experiences its own slow rearrangements over deep time. Long before any galactic collision arrives, the Sun's own gradual brightening will already be reshaping Earth. Within about 600 million years, rising solar output is expected to intensify weathering processes, disrupt the carbon cycle, and push global temperatures beyond what most complex life could tolerate. Earth's climate, so carefully balanced today, will face gradual but decisive transformation long before Andromeda ever comes into view. Earth's oceans may vanish within roughly 1 billion years, as the Sun's steady brightening finally overwhelms the planet's fragile water cycle. Heat will drive evaporation faster than rain can return moisture to the seas, thinning the oceans into vapor that slips away into space. Basins once filled with water may lie exposed and cracked, holding only the memory of tides that once shaped them. It becomes a slow farewell, written across hundreds of millions of years. Long before Andromeda ever arrives, a much smaller companion will complete its own descent into the Milky Way. The Large Magellanic Cloud, one of our galaxy's brightest satellite dwarfs, is losing energy to dynamical friction with every orbit it makes. Its path is expected to spiral inward until it merges completely with our galaxy's outer disk. This smaller union offers a gentler preview of the larger encounter still waiting ahead. That smaller merger could occur within about 2 billion years, arriving well before Andromeda's approach reaches its climax. Astronomers base the estimate on the dwarf's current mass, its distance, and the speed at which it circles us. Unlike the coming Andromeda encounter, this absorption involves a companion far smaller than the Milky Way itself. Even so, it will leave its own mark, stirring the outer disk and adding fresh stars to our galaxy's edge. Let warmth begin at the crown of the head, spreading down like sunlight, settling through still water. Feel it move across the forehead, easing the small furrow between the brows, then pooling along the jaw until the mouth softens on its own. Let it drift into the shoulders, loosening what the day left tightened there. Follow it down through the arms, into open palms growing heavy and warm, sinking further into rest with every breath. Gradual depletion of interstellar gas will slow the Milky Way's star formation across the coming billions of years. Each generation of stars locks a portion of that gas away, leaving less material behind for the next wave of birth. Star-forming clouds that once glowed brightly will thin and cool, producing fewer new suns with each passing eon. The galaxy will not stop making stars entirely, but its pace will steadily ease towards stillness. Sun-like stars will keep shining within the galaxy for billions of years yet to come. Stars of our sun's size burn their hydrogen fuel slowly, stretching their lives out over spans that dwarf human history many times over. Long after countless shorter-lived giants have flared and faded, these modest yellow stars will still glow with the same patient light. Their steadiness makes them some of the galaxy's most enduring companions through deep time. By the time Andromeda's disks finally overlap with our own, the Sun will have already become a white dwarf. Its nuclear fires will have gone out long before, its outer layers shed away into space, leaving behind a small, dense ember of what it once was. That faded remnant would drift through the merging galaxies as a quiet observer, no longer producing light through fusion, only slowly cooling across unimaginable stretches of time. Andromeda's presence in Earth's night sky will grow steadily larger across the billions of years ahead. What appears tonight as a soft smudge, visible only in dark skies, will slowly swell into a wide, glowing band stretching across the heavens. Each passing 100 million years will make its shape a little clearer, its light a little stronger. The change unfolds so gradually that no single lifetime could ever notice it happening. 2 billion years from now, Andromeda will already appear noticeably brighter than the pale smudge we know today. Its light will have grown strong enough to catch attention even without a telescope, a soft glow hanging low against the darkness. Anyone standing beneath that future sky would sense, without needing to be told, that something vast was slowly drawing nearer. The stars themselves would seem to be leaning toward each other. Stretching begins long before the two galaxies ever touch, as their outer halos start to feel each other's pull. Loose stars and thin trails of gas at the farthest edges of both galaxies will bend first, drawn gently out of their old orbits. This distant reaching happens quietly, almost invisibly, long before the bright spiral disks themselves come anywhere close. It is the first faint handshake of an encounter still billions of years from its heart. Dark matter halos surrounding both galaxies will begin to overlap long before their bright disks ever touch. These vast invisible envelopes extend far past the visible stars, unseen yet gravitationally powerful. Their quiet convergence marks the true beginning of the collision, unfolding in regions no telescope can directly observe. By the time starlight from each galaxy finally mingles, their dark matter will have already been intertwined for millions of years. 3.75 billion years from now, Andromeda will fill much of Earth's night sky. Its spiral form will stretch from horizon to horizon, no longer a distant smudge but a dominating presence overhead. Individual dust lanes and bright star-forming regions will become visible to the unaided eye. Standing beneath such a sky would feel like gazing into another galaxy's living structure hanging directly above. Computer simulations point to a first close passage occurring around 4 billion years from now. Researchers running these models track billions of simulated stars, watching how gravity reshapes both galaxies during this initial encounter. The passage will not be a collision in any violent sense, but a gradual gravitational dance as the two systems swing past each other. Afterward, both galaxies will separate briefly before gravity draws them back again. Gravitational pull between the two galaxies will draw out long streamers of stars and gas. These tidal tails will extend far beyond each galaxy's original boundaries, curling outward like luminous ribbons against the darkness. Stars caught within these streams will follow entirely new paths, no longer bound to their galaxy's familiar rotation. Such tails have already been observed in other merging galaxies throughout the universe. Somewhere in a quiet room tonight, a thin column of dust hangs suspended in still air, caught for a moment in a beam of light. It does not rush to settle. It simply drifts, turning without direction, in no hurry to arrive anywhere. Let your own thoughts move the same way now, unhooked, unweighted, floating without needing to land. There is only this drifting, this stillness, this slow turning toward rest. Streams of stars will spill outward from both galaxies during their closest approach. Some will trail far behind, marking the encounter's path across the sky like long, luminous arms. Others will loop back before eventually resettling into the merging system. These outward streams offer astronomers a visible record of gravity's unhurried negotiation between two vast structures learning to become one. The central black holes at each galaxy's heart will begin drifting toward a shared center, Sagittarius a star, and Andromeda's own central black hole will sink inward as gravitational friction gradually drains their orbital energy. This process unfolds across hundreds of millions of years, far too gradual for any single observer to witness directly. Eventually, both will approach the same forming galactic core. Triangulum Galaxy, the local group's third-largest member, may eventually be drawn into this developing merger. Its own gravitational bond with Andromeda could pull it along as the larger collision unfolds. Whether it merges directly or simply orbits the combined system for a time remains uncertain. Its presence adds another layer of complexity to an already vast gravitational story. Its precise role in this future encounter remains an active question within astronomy. Some models show it merging early, drawn in by Andromeda's stronger pull. Other models suggest it might drift past entirely, only loosely tied to the unfolding collision. Either way, its fate stays linked to the same gravitational dance shaping the rest of the local group. Direct collisions between individual stars will remain extremely rare throughout the entire event. Space between stars is so vast that even as galaxies pass through one another, their stars rarely come close enough to touch. A star crossing through the heart of another galaxy might pass entirely unobstructed, surrounded only by open darkness. It is galaxies colliding, not the stars within them. Vast interstellar distances mean that when two galaxies collide, it is gas that collides, not stars. Stars are so small compared to the space around them that direct impacts almost never happen. But the vast clouds of gas drifting between stars are far larger and far more likely to touch. These diffuse clouds, stretching across hundreds of light years, will be the first true casualties of the encounter. Colliding clouds of gas will trigger a widespread wave of new star formation. When two dense clouds compress against each other, gravity finds new opportunities to gather matter into place. Regions once calm and diffuse will collapse inward, sparking countless stellar nurseries. Within these compressed pockets, young stars will begin to form in unusually dense clusters, lighting up the collision zone from within. The initial encounter may spark a temporary burst of starbirth across both galaxies. Astronomers call this kind of event a starburst, when star formation rates rise far above their normal pace. For a cosmic moment, both galaxies could blaze with far more newborn stars than they hold today. This burst will not last forever, but while it does, the merging system may glow brighter than either galaxy alone. Massive new star clusters will form from clouds of gas pressed together by the encounter. Compression drives these clouds to densities far beyond their usual state, allowing gravity to pull matter into tight, glowing knots. Some of these clusters may rival the largest star groups known in either galaxy today. Over time, many stars born this way will drift outward, spreading gradually into the wider galactic structure. Spiral arm structures will begin to distort under the mutual pull of both galaxies' gravity. What were once smooth, sweeping curves will bend and stretch as tidal forces tug at their edges. Andromeda's arms and the Milky Way's arms will lose their tidy symmetry, twisting into looser, more tangled shapes. This distortion marks one of the earliest visible signs that both galaxies are beginning to change. Let your jaw loosen now, releasing the small tension gathered along its hinge. Let your eyelids rest, heavier than they have felt all day, needing no effort to stay closed. Behind them lies only a wide, dim field, dark and unmeasured. Let your brow smooth, the corners of your mouth loosen their hold, your whole face settling into stillness. Rest here, in that hushed space behind your eyes, wanting nothing further tonight. The Milky Way's disk will begin to warp during these early encounters. Instead of lying flat, its outer regions will bend upward and downward like the brim of a loosely held hat. This warping happens because gravity from Andromeda pulls unevenly across the disk's vast span. Astronomers see similar warps in other interacting galaxies today, offering a preview of what lies ahead for our own. Andromeda's own disk will warp in much the same irregular way. As the two galaxies exchange gravitational pull, neither will remain untouched by the other's mass. Andromeda's outer stars and gas will bend outward, tracing new, uneven curves across its structure. Both galaxies, once each cleanly spiraled, will begin to mirror each other's distortion. Long tidal tails will stretch far beyond both galaxies, reaching into intergalactic space. Streams of stars and gas, pulled loose by gravity, will trail outward like luminous ribbons unwound from their source. These tails may extend for hundreds of thousands of light-years, farther than the width of either galaxy itself. Such tails have already been observed trailing from other merging galaxies across the universe. Some stars may be flung entirely free, drifting alone through intergalactic space. Caught by a sudden gravitational push during close encounters, individual stars can gain enough speed to escape their home galaxy altogether. Once released, such a star would travel on, unbound to any galaxy, carrying its own small light into the dark between them. It becomes, in a sense, a traveler belonging to no place at all. Our solar system's distance from the galaxy's center may shift by a wide margin. Gravitational tugging during the encounter could nudge the Sun and its planets into a new orbit, farther out or closer in than today. Such a change would unfold across millions of years, imperceptible to any single generation. Yet across that span, the whole neighborhood of stars around us could look entirely unfamiliar. Compressed gas clouds could seed new stellar nurseries in places that once held only empty space between the arms. As gravity presses interstellar gas into denser knots, fresh pockets of star birth may ignite far from any previous pattern. Some of these new regions could appear beyond either galaxy's original disk, scattered like sparks flung from a larger fire. The galaxy's map of star-forming zones would look nothing like it does tonight. Earth's night sky would change continually through this stretch of the encounter, though no two nights would look identical. Andromeda's stars would spread wider, tangle with new streams of light, and shift position against the familiar backdrop. Bursts of new star birth might appear as fresh, bright points scattered unpredictably. Anyone watching across these ages would witness a sky in constant, gradual rearrangement. Individual star systems are far more likely to be swept into new orbits than torn apart outright. The vast emptiness between stars means gravitational nudges, not collisions, decide most of their fates. A star and its planets might travel enormous distances from where they began, yet remain entirely intact. Displacement, not destruction, defines the ordinary experience of a star caught within this merger. Some studies suggest a habitable planet could pass through this entire merger relatively undisturbed. Because stellar collisions remain so rare, a planet's day and night, its seasons, could continue with little interruption. Its sky would transform overwhelmingly, filled with unfamiliar light, yet the ground beneath it might stay steady. Such a world would carry on largely undisturbed amid a sky rewriting itself above. The merger will not directly threaten the survival of most planetary systems already in place. Even as galaxies pass through one another, planets tend to remain bound to their stars, following them wherever gravity carries them next. Threats to life would come instead from a star's own aging, its dimming or swelling over time. The collision itself, remarkably, poses little direct danger to worlds like ours. Let your breath find its own easeful pace, rising and falling without any effort from you. Notice the pause at the top of each inhale and the longer, looser release that follows it. Each exhale can stretch a little further than the one before, carrying tension out with it like a tide pulling back from shore. There is only this breath, and then the next, and nothing more required of you. Simulations show the two galaxies passing through each other multiple times before they finally merge into one. Rather than a single collision, the process unfolds as a series of approaches, retreats, and returns across great spans of time. Each pass loosens the galaxies' grip on their own shape a little further. What looks instantaneous from far away is up close a long unfolding rhythm of encounter and separation. A second close passage will follow the first, arriving after a gap of a few 100 million years. By then, both galaxies will have separated once more, only to feel each other's pull return. This second meeting will draw them nearer than before, their outer regions overlapping more completely than during the initial approach. Each return brings the two galaxies one step closer to their shared future. Each successive passage will disrupt the galaxy's original structures more than the last one did. Spiral arms will lose their clean curves, gas will scatter more widely, and stars will scramble further from their orbits. What began as two organized disks will become something looser and less defined with time. With every pass, the record of their earlier, separate shapes fades further into the past. Dynamical friction acts like a hidden brake, spanning the space between the two galaxies. As stars, gas, and unseen dark matter tug against each other, their swirling motion steadily bleeds into scattered heat and disordered energy. This drag builds with every pass, sapping speed from the galaxy's mutual orbit. Over hundreds of millions of years, that steady loss narrows the distance between their two hearts. Every close approach drains a portion of the galaxy's orbital energy, leaving them with less momentum to carry them apart again. Where their first swing might have flung them far into surrounding space, each later pass sends them only a shorter distance before gravity calls them home. The arcs between encounters shrink, pass after pass. In this way, distance itself becomes the resource that the two galaxies spend down together. Spiral morphology, so orderly today, will loosen into something far less structured as the encounters continue. The clean, sweeping arms that once traced each galaxy's rotation will stretch, fray, and fold in on themselves. What remains recognizable after one pass may blur entirely by the next. Astronomers who study these transformations describe the process as a gradual dissolving of familiar form into something new. Merging galaxies, observed across the universe, typically follow the same broad arc, spiral becoming elliptical over great stretches of time. Astronomers have watched this transition unfold in dozens of colliding pairs, each one trading its disk-like shape for a rounder, less structured form. The Milky Way and Andromeda are expected to follow this same well-worn path. Their future shape will resemble a glowing ball of stars more than the flat spirals we recognize tonight. Stellar orbits, once locked into tidy rotational lanes, will scatter into every possible direction as the merger deepens. Stars that circled their galactic centers in near-perfect unison will instead loop, tumble, and cross paths at odd angles. Order gives way to something closer to a swarm than a wheel. The organized spin that once defined both galaxies will dissolve into a looser, more random motion. The interstellar medium, the thin haze of gas and dust filling the space between stars, will grow turbulent as the two galaxies interlace. Clouds that once moved along smooth, predictable paths will instead churn, collide, and compress under mounting gravitational stress. Pockets of gas will heat, cool, and heat again in uneven cycles. This restless mixing sets the stage for dramatic changes still to come. Shock waves rippling through colliding gas will compress loose material into pockets, dense enough to collapse under their own gravity. Where two clouds meet at speed, pressure builds until matter packs tightly into knots capable of birthing new stars. These compressed regions become nurseries, seeding fresh generations of stellar light. Out of the disorder, something new begins to take shape. Feel the weight of your body settle a little further into the surface beneath you. Let your shoulders sink first, heavy and unhurried, followed by your arms, your hands, each finger loosening in turn. Your hips grow heavier next, then your legs, then your feet, each part giving its full weight over to whatever holds you. There is nowhere this heaviness needs to go, only down, only further, only here. Some models predict star formation rates spiking to many times their current level once the two galaxies fully interlace. Gas compressed by repeated collisions could ignite bursts of new stars at a pace unmatched in either galaxy's history. For a relatively brief cosmic interval, the merging system might blaze brighter than either galaxy manages today. Astronomers use the term starburst to describe such short, intense episodes of stellar birth. The two central supermassive black holes will spiral closer together as the surrounding stars and gas settle around the merging cores. Each carries the gravitational imprint of its home galaxy, dragging nearby material inward as it moves. Over time, their paths will tighten into a slow gravitational embrace. This inward pull marks one of the final acts in the two galaxies becoming one. Inflowing gas, drawn toward the merging cores, may fuel a marked rise in activity within one or both black holes. As material spirals inward, it heats and glows, forming bright accretion disks around each hungry center. Astrophysicists studying similar systems have observed this pattern before, in galaxies caught mid-collision elsewhere in the universe. For a time, each black hole could shine as though newly awakened. Enhanced feeding of this kind could trigger a temporary phase astronomers call an active galactic nucleus. During such an episode, a black hole's surroundings radiate with extraordinary brightness, outshining entire stellar populations nearby. This phase would not last indefinitely, since activity of this intensity tends to fade as fuel is consumed. Even so, while it lasts, the galactic center would blaze with unusual intensity. During this phase, the merging system may come to resemble what astronomers classify as a luminous infrared galaxy. Such galaxies radiate enormous energy, much of it hidden within dust and gas rather than visible light. Their brightness often comes from a combination of vigorous star formation and an actively feeding black hole. Seen from afar, the merging Milky Way and Andromeda might glow with a similar hidden intensity. The complete merging process, from first approach to full settling, is expected to span more than 1 billion years. Cosmic transformations at this scale rarely happen quickly, unfolding across stretches of time that dwarf any single human lifetime many times over. Multiple passes, tidal disruptions, and slow settling each demand their own long intervals. Such vastness folds entire epochs into what will eventually become a single unified galaxy. The Sun may be flung into an entirely different region of the merged galaxy than the one it occupies today. Interactions during the collision could carry it far from its familiar orbit toward the outer edges or deep into unfamiliar territory near the core. Its precise fate remains impossible to predict with certainty, since so much depends on the exact timing of each close encounter. Wherever it ends up, it will still be shining, carried along by forces far larger than itself. A small chance exists, according to a handful of models, that the solar system could be ejected from the galaxy entirely. In such a scenario, the Sun and its planets would travel not merely to a new region, but out beyond the galaxy's edge altogether, into the emptiness between galaxies. This outcome sits at the far edge of possibility, rather than the center of it. Most simulations still keep the Sun somewhere within the newly formed galaxy's boundaries. That ejection probability is estimated at under 5%, a low but not impossible figure within the range of modeled outcomes. Most calculations place the Sun's likely future safely within the merged galaxy, whatever new shape that galaxy eventually takes. Even the least probable outcomes deserve mention, if only to show how many paths this long story could still take. The odds favor staying, though the universe rarely promises certainty. Certain simulations suggest the Milky Way's disk could partially survive the encounter, retaining traces of its former spiral shape even after merging. Not every structure needs to be destroyed for a galaxy to be transformed. Some features persist in altered form. A faint echo of today's spiral arms might remain detectable within the merged galaxy's outer regions. The past, in this sense, would not vanish so much as fold into something new. Somewhere beyond this room, a low hum rises and fades, perhaps a distant road, perhaps only the house settling into the night. Let it arrive without asking anything of you. It swells for a moment, then recedes, like breath moving in and out of some larger unseen body. There is no need to follow where it goes. Let your ears rest as loosely as your hands, and let that far-off sound carry you further from waking, one wave at a time. Other simulations propose that the collision's exact geometry remains genuinely uncertain, with outcomes varying based on assumptions no one can yet fully confirm. Small differences in mass, angle of approach, or velocity can shift the entire sequence of events that follows. Astronomers continue refining their models as better measurements of Andromeda's motion become available. The broad outline is clear, even while many fine details of this future remain unwritten. Two supermassive black holes, once separated by thousands of light-years, will eventually spiral together and merge into a single, far larger black hole. This union marks the true endpoint of the two galaxies' long gravitational dance. For eons, the black holes orbit each other, drawing closer with each pass until only one remains. What was once two centers of gravity becomes one, anchoring the newly formed galaxy at its heart. A burst of gravitational waves should ripple outward at the very moment those two black holes complete their union. These ripples, tiny distortions in the fabric of space itself, would spread outward at the speed of light. Detectors built by human hands, tuned to catch such faint signals, could in principle register the event from immense distances. The waves themselves carry no light, only a subtle stretching and squeezing of space as they pass. 10 million times the mass of the Sun, or perhaps more, could describe the black hole born from this cosmic union. Sagittarius, a star, and Andromeda's own central black hole, each already millions of times more massive than the Sun, would combine their bulk into one immense object. Such a merged black hole would rank among the largest in the observable universe. Its gravity would still, in the end, remain bound to the scale of a single galaxy. Gravitational wave emission may impart a recoil kick to the newly merged black hole, sending it drifting away from the galaxy's exact center. This kick arises because the waves themselves can carry momentum asymmetrically, like a quiet push in one direction. Depending on the black hole's masses and spins, that kick could be small or, in some models, surprisingly large. Either way, the merged black hole may spend a long stretch of time drifting back toward the galaxy's core. Remaining gas will be gradually consumed by new stars or expelled outward by the energy released from black hole activity. Each process draws down the reservoir that once fed star formation across both galaxies. Winds driven by the active black hole can push gas clear of the galaxy entirely, while dense clouds elsewhere collapse into fresh stars. Over time, less and less raw material remains to build anything new. The merged galaxy will gradually take on a smoother, more rounded elliptical shape, quite unlike the spiral disks it once was. Where organized arms once wound outward, a broad glowing ellipse will remain. Stars that once followed neat orbital paths will instead move along more random, tangled routes. The transformation unfolds over hundreds of millions of years, long after the last close passage between the two original galaxies. Star formation rates will fall sharply once the shared gas reservoirs of both galaxies are finally exhausted. The brilliant bursts of new stars that marked the early merger will fade into a quieter, dimmer rhythm. Fewer massive blue stars will ignite, and fewer bright nebulae will glow with fresh starlight. What remains will be an older population of stars, shining across a quieter, dimmer galaxy. Astronomers have given this future merged galaxy an informal nickname, calling it Milky, a blend of Milky Way and Andromeda. The name captures both origins in a single word, honoring the two galaxies that once moved separately through the local group. No formal designation yet exists, since the merger remains billions of years away. For now, the nickname offers a simple way to speak of a galaxy that does not yet exist. Faint shell-like structures of stars, often seen around other elliptical merger remnants, may form around this future galaxy as well. These shells appear as delicate, curved arcs of stars, layered like the rings of a cut stone. They form when stars flung outward during the merger fall into overlapping loops. Astronomers have already observed similar shells surrounding elliptical galaxies elsewhere in the universe, evidence of mergers completed long ago. Let warmth begin somewhere small, perhaps at the center of your chest, and let it spread outward from there. Feel it move into your shoulders, loosening whatever they have carried all day. Let it flow down through your arms, into your hands, until your fingers rest heavy and unclenched. Let the warmth continue into your hips, your legs, your feet, until every part of you feels held by its glow. Stay here, warm and unhurried, for as long as you like. Milky's total stellar mass will combine every star born across two separate galactic histories. Old red dwarfs, young blue giants, and countless stars in between will belong to one shared population. The Milky Way's stars and Andromeda's stars, once counted separately, will simply become part of the same vast whole. Together they may total more than 1 trillion suns spread across a single unified galaxy. Organized spiral arms, once the signature of both galaxies, will not survive the merger. The graceful curves of star-forming material will dissolve into a smoother, rounder shape. Where dust lanes and bright arms once traced clear patterns, only a diffuse glow will remain. This transformation echoes what astronomers observe in other galaxy mergers across the universe, each ending in a similar loss of structure. Stars that once circled their galaxies in orderly disks will begin moving along tangled, looping paths instead. The Milky Way's disk and Andromeda's disk both spun with a shared sense of direction, stars orbiting together like dancers in step. After the merger, that coordination breaks down. Individual stars follow elongated, crossing orbits, and the galaxy's motion becomes a kind of stellar traffic without lanes. A much reduced rate of star formation may persist, fueled only by whatever gas remains after the collision concludes. Isolated pockets of leftover material could still collapse under gravity, sparking occasional new stars within the merged structure. The pace will be far slower than during the earlier starburst, a trickle rather than a flood of new light. Even this trickle will thin further, as available gas keeps dwindling with time. Globular clusters from both galaxies will become part of a shared stellar halo surrounding Milky. The dense ancient clusters that once orbited the Milky Way and Andromeda separately will intermingle within this outer region. Some hold stars nearly as old as the universe itself, formed long before either galaxy took shape. Within the merged system, these clusters will continue circling together, tracing slow, wide arcs around one shared galactic center. The dark matter halos of both galaxies will fully merge into one larger halo surrounding Milky. Long before their visible stars ever met, this unseen material had already begun overlapping and combining. Far more massive than all the stars combined, it provides the gravitational scaffolding holding the entire galaxy together. Every star and cluster will continue moving within its silent, unseen grip. Within roughly 7 billion years, the Milky Way as a distinct galaxy will effectively cease to exist. Its stars, its gas, and its structure will have become fully woven into Milky. The name Milky Way will remain useful only as a historical marker describing what once existed before the merger. No boundary will remain to mark where one galaxy ended and the other began. Astronomers define the merger's completion by the point when the combined system finally reaches dynamical equilibrium. Equilibrium means stars no longer show signs of the collision's disruption, moving instead in steady, balanced orbits throughout the galaxy. Reaching this state can take several billion years beyond the initial collision, long after the dramatic tidal tails have faded from view. Once achieved, Milky will resemble other mature elliptical galaxies observed today. Milky is expected to become the dominant galaxy of a transformed local group. Carrying the combined mass of both the Milky Way and Andromeda, it will outweigh every neighboring galaxy by a wide margin. Smaller galaxies that once orbited either system will find themselves circling this single massive body instead. Its gravity will shape nearly everything nearby, much as Andromeda and the Milky Way once shaped their own smaller satellites. Local group dwarf galaxies face a similar future within Milky's growing gravity. The Magellanic Clouds, or the remnants of the Sagittarius dwarf, may eventually spiral inward and merge with the larger body over time. Gravity will pull these smaller systems closer with each pass, stretching them into thin streams before fully dissolving them into Milky. Over vast stretches of time, the local group may simplify into just one great galaxy. Somewhere in this stillness, an ember dims from orange to amber, then to gray ash, its glow fading without any need to be tended. Let each breath fall the same way, a little dimmer than the last, until the fading itself becomes restful. Your shoulders loosen, your thoughts lose their edges, like coals cooling in a hearth, in no hurry to become anything else tonight. Dwarf galaxies still tracing orbits around Milky will spiral steadily inward, their paths slowed by dynamical friction, a gravitational drag caused by their own passage through the surrounding halo of matter. Each pass loses a little momentum. Over vast stretches of time, these small companions drift closer, their orbits tightening until they are finally drawn into the growing body they once merely circled. Triangulum Galaxy, the modest spiral once keeping its distance from both the Milky Way and Andromeda, may eventually be captured by Milky's growing gravity. Its future path remains uncertain in detail. It might swing into a long orbit around the merged galaxy, or it might eventually be drawn inward and absorbed entirely, joining the same fate as its two larger neighbors. Far beyond the borders of the local group, accelerating cosmic expansion will carry other galaxy clusters ever further away, eventually beyond the reach of any possible observation. Space itself continues stretching, faster with each passing age. Distant clusters that once appeared as dim smudges in telescopes will fade entirely from view, their light forever outrun by the growing space between. In that distant era, Milky may stand as one of remarkably few galaxies still visible from within a transformed local group. Its former neighbors, carried off by the universe's expansion, will have slipped beyond any telescope's reach. What remains nearby will mostly be Milky's own captured satellites, orbiting a galaxy that has, in a sense, become an island unto itself. Overhead, in that far future, only Milky's own stars will light the night, since more distant galaxies will have drifted past the horizon of what can still be seen. Anyone standing beneath that sky would find it dominated entirely by one galaxy's light. The countless external companions we see tonight will simply no longer be there to notice. The sun, having long since become a cooling white dwarf, may still trace its own path somewhere within Milky's enormous structure. Its light will have dimmed to a dull ember of what it once was, yet its orbit continues, carrying that small ember of a star, through the merged galaxy for ages beyond ages, one point of light among billions of others doing the same. Stellar remnants, white dwarfs, neutron stars, and black holes will gradually come to outnumber the galaxy's living, shining stars. Each represents a star that has finished its life, leaving behind only its dense, dark core. As the eons pass, more and more of Milky's mass will exist in this dimmer form, present but no longer burning. Metallicity across the merged galaxy will continue rising as each generation of dying stars scatters heavier elements back into the surrounding gas. Later generations of stars form from this enriched material, carrying more carbon, oxygen, and iron than the stars before them. Over billions of years, this slow recycling steadily changes the chemical character of everything born within Milky. Within several tens of billions of years, star formation may fall almost silent across Milky, as its reserves of usable gas grow increasingly scarce. The bright bursts of new stars that once accompanied the collision will have long faded into memory. What remains will burn on, an aging galaxy coasting toward its own kind of stillness. Massive blue stars, always the quickest to burn through their fuel, will begin to vanish first from Milky's population. As each one dies, the galaxy's light shifts away from that hot white-blue glow of youth. What remains leans toward amber and rust, the hue of stars built for long, unhurried lives. Star by star, Milky will warm in color, even as its overall light grows dimmer. Let your jaw loosen, just slightly, the way a hand opens when it finally stops holding something. Feel the weight sink into your eyelids, heavier now than they were a few minutes ago. Behind your closed eyes, there is only a wide, warm darkness with nothing asking to be seen. Let your face rest there, unclenched and unwatched, simply held by the dark. Burning far more conservatively than their brighter kin, red dwarf stars will keep glowing for trillions of years after the merger fades from memory. These small, dim stars use their fuel so sparingly that most have yet to finish even a fraction of their lives. Long after brighter stars have died, red dwarfs will still be present everywhere, tiny embers scattered across Milky's vast structure. Astronomers have a name for what Milky eventually becomes: a red and dead elliptical galaxy. Red, because its remaining stars burn in warmer, cooler tones. Dead, not in decay, but in the sense that new star birth has largely come to an end. It is a galaxy that has finished becoming, and now simply endures. Elliptical galaxies of this kind typically show little to no ongoing star formation, and Milky will follow that same familiar pattern. Their reservoirs of cold gas, the raw material stars are born from, have long since been used up or blown away. What stars remain simply age together, no longer joined by newcomers. It becomes a fixed population, unchanging in its makeup. Near the galactic center, stellar density may climb substantially after the merger runs its course. Stars drawn inward by gravity over the ages tend to crowd together, forming a denser, brighter core than either progenitor galaxy once had. Where the Milky Way's own center once held millions of stars, Milky's new heart may hold many times that number, packed closely in the dark. A single black hole, larger and more massive than either of its two progenitors, will anchor the center of this newly merged galaxy. Formed from the eventual joining of Sagittarius, a star, and Andromeda's own central giant, it will sit at the heart of Milky as the deepest gravitational anchor, holding the galaxy's inner stars in wide, patient orbits. Occasionally, a star wandering too close to that great dark center will be pulled in, captured into a tight orbit, or torn apart by gravity's uneven pull. These events remain rare, scattered across immense stretches of time. Yet even in a mostly still darkened galaxy, the black hole at its heart still has moments of brief, dramatic activity. These tidal disruption events, when a star is shredded by the black hole's gravity, can still send a brief flare of light across the otherwise darkened galaxy. For a short while, the disrupted star's material glows brightly as it spirals inward and falls beyond view. Such flares offer rare, fleeting punctuation marks in a galaxy that has otherwise grown remarkably still. Over the passing eons, Milky's overall luminosity will decline steadily as fewer young stars arise to replace the ones that fade. The blazing brightness of its early merger years, full of starbursts and flares, gives way to a longer, dimmer glow. Each passing billion years, the galaxy grows a little darker, its light folding into the vast surrounding night. Globular clusters that survive the collision will not vanish into the merger swirl. Instead, they will continue their broad orbits, circling Milky's center, much as they once circled the separate Milky Way and Andromeda. Some of these clusters hold stars nearly as old as the universe itself. They will persist as dense islands of light orbiting through emptying space, long after their parent galaxies have blended into one. Gas drifting through the newly formed galaxy will not remain as thick or as warm as it once was. With each passing age, it spreads thinner, cooling toward the temperature of the surrounding dark. Fewer dense clouds will form, and fewer stars will be born from them. What gas remains will drift almost undisturbed, a faint breath spread across vast empty distances. For now, let your attention rest on the breath alone. Notice how it arrives without effort and how it leaves just as easily. Each exhale can grow a little longer than the one before it, unwinding something held in the chest. There is no need to count them, only to let them come, one after another, carrying you a little further from waking. Star formation, where it still occurs, will be limited to remaining pockets of gas dense enough to draw together. These are rare exceptions, scattered through a mostly settled galaxy. Each pocket kindles for a while, then subsides again into stillness. Across most of Milky's vast expanse, no new stars will ignite. The merged galaxy's total mass should remain fairly steady from this point onward, barring some later encounter with another wandering galaxy. Its stars, gas, and dark matter settle into balance, neither growing much nor shrinking. Milky becomes, in a sense, a finished structure. Whatever changes come after this will unfold from within, over immense stretches of time. Planets that endure this far will circle stars growing steadily older and steadily more alone. Their neighboring systems have drifted farther apart or faded entirely. Where a sky once held many bright companions, only a handful of distant points may remain. Each surviving world turns around its aging sun, far from any other living light. Habitable zones around these remaining stars will not stay fixed in place. As a star ages, brightens, or cools, the band of warmth suitable for liquid water shifts outward or inward. A world once far too cold might, in time, warm into livability. Another, once temperate, may find itself scorched as its star swells with age. Any life that persisted this far into the galaxy's story would face a universe growing sparser and darker by the age. Neighboring stars would be fewer, dimmer, farther between. The night sky above such a world would hold far less light than it once did. Existence, if it continued at all, would unfold beneath an increasingly empty heaven. Across trillions of years, star formation throughout Milky will taper toward its effective end. The last reserves of usable gas will thin past the point of collapsing into anything new. What stars remain will continue burning or fading without replacement. The galaxy's long story of birth, in this sense, draws to its close. Hydrogen, the element that fueled nearly every star to ever shine, will eventually run its course throughout the merged galaxy. What began as vast primordial clouds, gathered since the universe's earliest ages, will at last be spent. Stars will continue to shine for a long while, yet on what remains, but the deep well that fed them all is destined, eventually, to run dry. Red dwarfs, the smallest and most numerous stars ever born, will come to dominate what remains of Milky stellar population. These faint red suns burn far longer than their brighter cousins, sipping hydrogen at a fraction of the rate. Long after larger stars have died, red dwarfs will still glow, faint but steady. Across the galaxy's remnant structure, they will vastly outnumber every other surviving star. Stellar mass black holes will grow steadily more common as one massive star after another completes its life. Each collapse leaves behind a small, dense point of gravity, invisible except for its pull on nearby matter. Over eons, these remnants accumulate throughout the galaxy's structure. What was once a population of luminous stars slowly gives way to a scattering of silent, unseen cores. Neutron stars, born in the violent deaths of massive stars long past, will litter the galaxy's remnant structure like scattered embers. Each one is impossibly dense, a sun's worth of mass compressed into a sphere the size of a city. Some spin rapidly, sweeping faint beams of radiation across space. Others cool in silence, drifting unseen among the galaxy's fading light. Let your body grow heavy now, sinking a little deeper into whatever is holding you. Feel the weight settle first in your shoulders, then your arms, then your hands, each one heavier than the last. Let your legs grow heavy too, sinking into the mattress beneath them. Your head rests, full and still, cradled by whatever supports it. There is only this weight, this stillness, this slow settling into rest. Type ES supernovae, the bright explosions once produced by dying white dwarf systems, will become progressively rarer as their source populations dwindle. These explosions required a white dwarf drawing matter from a companion star until reaching a critical mass. As fewer such pairings remain, fewer explosions occur. The galaxy's long history of bright standard candle flashes drifts toward a final close. Planetary nebulae, the glowing shells once shed by dying sun-like stars, will appear less and less often across Milky. Each nebula formed briefly, a colorful cloud of expelled gas lit by the exposed core of a dying star. As fewer stars remain in the stage of life that produces them, these luminous shells grow scarce. The galaxy's sky, once dotted with such fleeting ornaments, will hold far fewer of them. Brown dwarfs, too small ever to ignite full nuclear fusion, will continue radiating faint warmth across almost unimaginable spans of time. These dim, failed stars glow not from fusion but from the slow leak of heat left over from their formation. That heat fades exceedingly slowly, allowing brown dwarfs to remain faintly visible for trillions upon trillions of years. Long after brighter stars have died, these dim embers persist. Gravitational encounters between stars, rare but cumulative, will gradually fling some stars entirely out of the galaxy's outer reaches. Each close pass between two stars exchanges a small amount of energy, and over enough time, some stars gain enough to escape the galaxy's pull altogether. These escaping stars drift outward into the emptiness between galaxies. One by one, the outskirts of Milky thin as its stars scatter into the dark. Other stars, following the opposite path, will sink further toward the galactic center as gravitational encounters redistribute their orbits. Energy lost in these encounters draws such stars inward, tightening their paths around the galaxy's dense core. Over time, the center grows more crowded, while the outskirts grow more sparse. The galaxy's stars, in this long migration, divide between those flung outward and those drawn ever inward. Overall stellar density will decline across Milky as its outer regions gradually empty themselves of stars. This process, astronomers call evaporation, unfolds not through any single collapse, but through countless small gravitational nudges compounding across billions of years. Stars ejected outward and stars drawn inward. Both remove mass from the galaxy's outer disk. What remains, over unfathomable time, becomes a smaller, denser, more concentrated remnant of what once was a vast galaxy. The central black hole at Milky's core continues to grow, drawing in whatever nearby matter remains within its reach. Wandering gas clouds, stray stars, and stellar remnants that drift too close eventually spiral inward and merge with its mass. This growth proceeds unevenly, with long stretches of near stillness between each meal. Across trillions of years, though, the black hole's mass keeps its slow upward climb. Over immense stretches of time, black holes may come to hold most of the galaxy's remaining mass. As ordinary stars burn out, collapse, or drift away, the black holes left behind neither fade nor scatter as easily. Stellar mass black holes, along with the giant one at the core, persist long after their brighter neighbors have gone dark. In this way, mass steadily concentrates into objects that once seemed rare exceptions. Theoretical physics predicts that even black holes will eventually fade away, losing mass through a process called Hawking radiation. First described by physicist Stephen Hawking in the 1970s, this radiation arises from quantum effects near a black hole's boundary. It causes black holes to lose mass at an extraordinarily gradual rate, far too small to detect on any time scale within our current reach. In principle, every black hole within Milky would eventually succumb to this same dissolution. That evaporation process would take almost inconceivably longer than the universe has existed so far. A black hole with the mass of our merged galaxy's core would require a duration beyond ordinary comprehension to fully dissipate, stretching across timescales written not in billions, but in numbers with far more zeros. The universe today is roughly 13.8 billion years old, yet Hawking radiation would need vastly longer still to finish its work. Such numbers exceed ordinary imagination, marking one of the longest timescales physics has ever proposed. Somewhere past the edge of hearing, a low hum rises and fades, like a sound the night makes as it settles. Perhaps it's wind pressing against a window, or the house shifting, its boards finding new rest. That sound arrives, holds a moment, and drifts away again, leaving only stillness and your own steady breath. Let it come and go, again and again, until your body forgets there was ever anything to listen for. Cosmic expansion, still accelerating, will continue pulling distant galaxies away from Milky at ever-increasing speeds. Structures that once anchored the wider local group will drift beyond any possible connection, their light stretched and their presence diminished. Milky itself, bound tightly by its own gravity, will remain intact even as everything beyond it recedes. Over enough time, the galaxy that outlived its neighbors will find itself essentially alone in an emptying universe. The observable universe's horizon will keep contracting in relative terms, even as Milky's physical size remains essentially unchanged. Dark energy, driving space itself to stretch faster and faster, pushes the boundary of what can ever be seen closer and closer inward. Galaxies once visible from within Milky will cross beyond that boundary, their light forever unable to arrive. What began as a universe filled with countless visible galaxies will, from Milky's vantage, appear to empty itself. Ancient light, the cosmic microwave background, will grow undetectably dim across these distant eras. Stretched by continued expansion, its wavelength will lengthen until its signal all but disappears into the noise of empty space. Instruments that once mapped this ancient glow with precision would find by then essentially nothing left to measure. One of the universe's earliest messages, carried since its infancy, will have effectively gone silent. Milky may endure as a solitary island universe for the remainder of cosmic time, cut off from every external structure it once shared a local group with. This phrase, one astronomers used long ago to describe galaxies as separate cosmic worlds, returns with new meaning in this future. No merger, no visitor, no distant light will arrive to disturb its isolation. Whatever unfolds within Milky from this point onward will unfold entirely on its own. Looking outward from within Milky, an observer would eventually find almost nothing beyond its own edge, only a dark and star-poor sky stretching in every direction. The countless galaxies that once filled the ancient night would have receded beyond reach, their light stretched past any hope of arrival. Only Milky's own stars, however diminished, would remain to light that endless dark. It would be a sky nearly empty, holding within it the last remaining light of a single galaxy. Elsewhere in the universe, radio and infrared telescopes trace the slow churn of gas inside galaxy pairs already locked in collision. These instruments read the shifting temperature and motion of hydrogen clouds as two disks pass through one another. Astronomers watching these distant ongoing mergers gain a living reference for what the Milky Way and Andromeda will eventually undergo. Every observed pair adds one more data point to a shared cosmic pattern. Machine learning now lets researchers test thousands of possible merger scenarios in the time it once took to run a single simulation. Algorithms adjust mass, angle, and velocity across countless variations, searching for outcomes that match what telescopes actually observe. This accelerates the search for the most likely path the Milky Way and Andromeda will follow. It turns a slow, patient science into something closer to rapid exploration. Astronomers continually refine these merger models whenever new observational data becomes available. Each fresh measurement, whether from a satellite or a ground-based telescope, adjusts the predicted timeline by some small margin. Picture of this future collision has grown sharper with every passing decade, though it remains by nature always provisional. Science approaches this ancient future the same unhurried way it approaches everything else. Any human-made spacecraft that somehow endures across billions of years would face a fate shaped almost entirely by its position when the merger unfolds. A craft drifting near the outer edges might be flung outward along a stretching tidal tail. One nearer the core could be drawn inward, swept toward the deepening gravity well. Its story, like so much else in this future, would depend less on design than on simple location. The story of the Milky Way's slow collision with Andromeda is really the story of the universe doing what it has always done, gathering, merging, and reshaping itself across unimaginable stretches of time. Long after tonight, this quiet rearrangement will continue, indifferent and patient, the way it has since the first galaxies formed. You exist for this brief moment inside one small chapter of that vast unfolding. Rest now and let the rest of the story carry on without you. Good night.